Hello everyone, welcome to today's video. We'll get right into it. Today we're going to be talking about rational functions. We'll define them, we'll look at their domain. There's some interesting stuff that can happen here. We'll look at this arrow notation, and this is just a way that we can talk more specifically about vertical and horizontal asymptotes. And then we'll talk about slant asymptotes as well. We'll talk about removable discontinuities, or what we sometimes call as holes in the graph. And then we'll look at the intercepts of rational functions so that we can try and graph them once we're all done here. So we'll start with the definition. A rational function is a function, and it is the ratio of two polynomials. So it can be represented here. We have f of x as being the ratio of two polynomials, p of x and q of x, and we just want to make sure that q of x isn't equal to 0, either just it's not the zero constant function, or that we're very careful with when we plug in values to f of x that we don't accidentally divide by 0 once we plug things into q of x here. So that's kind of where we will focus our attention. We'll look at a couple of examples here. The first one is f of x is equal to x over 5x plus 11. So it's not really the numerator that we're concerned about. The numerator can be 0. 0 divided by anything is just 0. It's the denominator being 0 that we need to be careful. So what we can say is, okay, if 5x plus 11 were equal to 0, then that would be bad news. Or we can say not equal to 0, and either way we can solve. We just need to keep our logic consistent with how we're thinking about it here. So we will subtract 11 from both sides, and we'll get 5x is equal to negative 11. We'll divide both sides by 5, and we get that x is not equal to negative 11 over 5. So if we did try and plug that number in, we would end up dividing by 0. So if I'm going to try and just kind of write the domain here, the domain for this rational function is going to be anything from negative infinity all the way up to negative 11 over 5. And then we'll skip over that. We'll pick it right back up at negative 11 fifths and go to positive infinity. It's going to make that a little better. Well, it wasn't that much better. Good enough. So there's the domain. It's essentially all real numbers, but we just need to pluck out this point that would cause division by 0. So in this next one here, we have g of x equal to x minus 5 over x squared plus x minus 6. We're just going to use the same logic here. If x squared plus x minus 6 was equal to 0, then we would end up dividing by 0. So we can say not equal to 0, and we can just kind of use our logic from there going forward. But if I factored this, we would get x, let's see, plus 3, x minus 2, x squared. Yeah, that should get us what we want here. So this tells me that x plus 3 cannot be equal to 0, and x minus 2 cannot be equal to 0. So x can't be equal to negative 3, and x can't be equal to 2. So here there are going to be two spots that we need to remove from the domain here. So if I want to write the domain, we're going to be looking at negative infinity up to negative 3, and then we need to jump over negative 3 until we get to 2, and then we'll union that together with 2 to positive infinity. So kind of had to go into the next line there, but hopefully you get the point. Here's the domain for G. Here's the domain for F. So let's take a look at this arrow notation here. And this is just a way that we can talk about numbers approaching some value or inputs approaching some value without ever actually attaining that value. First we have this x arrow a with this superscript with a negative sign up there. And that means that we're approaching a from the left. So our inputs are approaching some value a. It could be 2, it could be negative 5, just some number. We're talking about the inputs getting closer and closer without actually being a itself. So here we see that this says x approaches a from the left. X is smaller than a, but close to a. And we can do the same thing coming from the other direction. So if we have this a to the plus sign, it means that we're coming in from the positive side. We're thinking about approaching a with x values being bigger than a, but close to a. And then we can think about doing the same thing as we go out to positive and negative infinity. X can get infinitely large, it increases without bound. So remember that infinity isn't a number. It's nothing that we can actually plug in anywhere. It is just an idea. It's just a direction that we can walk. I often say here, we're just walking in the positive x direction forever, and we'll think about maybe what happens to the output values there. And then similarly with x approaching negative infinity, it's decreasing without bound. It is just getting bigger and bigger in the negative direction. But again, these are just directions we can go. They aren't numbers that we can attain. So all of those ones up there all have to do with our input values, either approaching some number from each side or going out to positive and negative infinity, just increasing or decreasing without bound. These last three here all have to do with the output values. So the first one here, this is saying the output values are approaching infinity. They are increasing without bound. The second one, f of x approaching negative infinity, says they are going down and approaching negative infinity. They're decreasing without bound or getting larger in the negative direction. And then we can also talk about it approaching some value a. We don't really talk about it approaching from the left or the right because that's more of an up and down sort of thing, but we don't really care when we're talking about f of x approaching some value. We just care that it is approaching some value. So we'll take a look at an example here, and that'll lead us into the reason that we're talking about this notation, which is asymptotes. But here's the graph of f of x equals 1 over x, and I often use this graph or its relative 1 over x squared to help me think about the behavior of different graphs here. But what we have is that just looking at what happens near some different values. So this is saying this x is approaching 0 from the right hand side. So we're talking about values getting closer and closer and closer to 0, coming in from a positive direction where values are bigger than 0. Well, we can see here that that means that f of x is shooting off to positive infinity here. So hopefully that is clear from the graph. If we take a look at what is happening near x on the left side, on the negative side there, well, we can see that the f of x values are just decreasing without bound. They are going to negative infinity. So that is how we might write down some of this, or some of these ideas with the notation here. And then as we talk about maybe the input values here, we've got x growing without bound to positive infinity. Well, what's happening to the input values here? We can see that they're getting closer and closer and closer to 0. But will they ever actually be 0? Think about plugging numbers in here. Any number that you plug in is always going to result in, or any positive number you plug in will always result in a positive number. So it'll never actually equal 0. Any negatives that we plug in, we'll talk about that one next. But here what we have is that the outputs are approaching 0. As the inputs grow without bound, and then going in the other direction here, as the inputs are headed off to the negative infinity direction, we can see that all of the results are negative, but they are also approaching 0. They'll never actually hit 0. If you think about plugging in bigger and bigger negative numbers here, the result will always be negative, but will never actually be 0 itself. So here we are approaching 0. They're kind of coming in from different directions. One's attacking 0 from the top, one's attacking 0 from the bottom, but that's okay. They're both getting closer and closer to 0. So like I said, what we have here are some asymptotes. So we've got a vertical asymptote and a horizontal asymptote, and we are defining them by using this arrow notation here. So a vertical asymptote of a graph is the line x equals a. So when we're asked to state these asymptotes, either vertical or horizontal, we'll be asked to give the line x equals a, where a is whatever number. But this is where the graph tends towards positive or negative infinity as the input approaches a from either the left or the right. So looking back on this example, we're going to see this one again here in a second, but as we're approaching, from the right-hand side, it's going to positive infinity. From the left-hand side, it's going to negative infinity. They could both be going the same direction. We'll look at some examples like that in just a minute here. But those are the vertical asymptotes, and then the horizontal asymptote is the line y equals b. So remember, x equals a, x equals any number gives you a horizontal line. Y equals whatever always gives you a horizontal line. Hopefully I said that right. This is a vertical line. This is a horizontal line. But this is where the graph of the approaches the line as the inputs increase or decrease without bound. And so we write, as x is approaching either one, the output value is approaching just some number b here. So in the previous example, I think we're going to see this one again right now. But instead of looking at the output values, we're looking at the input values going out, and then the output's getting closer and closer to some number 0. So here we can see that. So like I said, this just the graph of 1 over x again here on the left. If I'm looking for the vertical asymptote, it is going to be this line right here, where I can see the values are getting closer and closer without ever actually touching that vertical line. And this is the line x equals 0. That is where the vertical asymptote is. The horizontal asymptote, again, is at 0. We can see that as x grows without bound in either the positive or negative direction, the outputs are just getting closer and closer and closer to 0. So here we have the horizontal asymptote as the line y equals 0. A little bit more interesting over here is the graph of g of x being the ratio of 3x minus 1 over x minus 2. So here we can see there's a vertical asymptote, not at 0, but it's kind of shifted over a little bit, and we can talk about shifting these graphs around from the kind of the parent function 1 over x here. We have a vertical asymptote here at the line x equals 2. So that would not be part of the domain here, and we can see if we're looking, if we did try to plug 2 into this function, we'd end up dividing by 0, which is why we have a vertical asymptote here. Whoops. And then the horizontal asymptote is this line, y equals 3. It has been shifted up 3 units here. So there we go. We've got a couple of different graphs. So you can see their asymptotes at different places. Yeah. So next we'll take a look at removable discontinuities here. So we'll read the definition, and there's a lot of words here, and we'll put them all together. We'll look at the example, and hopefully they make sense. I think it says exactly what we want. There's just a lot of words to go through. But a removable discontinuity occurs in the graph of a rational function at x equals a if a is a 0 for a factor in the denominator that is common with a factor in the numerator. So we're looking at some common factor once we factor the polynomials in the numerator and denominator. And that common factor cancels completely in the denominator when we simplify the rational expression. So we also call that a hole in the graph. So there's different ways that when we're looking at the domain of this rational function that we can get different looking things that happen in the graph here. So one of those things is going to be a vertical asymptote, which we kind of already saw. The other thing is going to be a removable discontinuity, which we'll see right here. So what we're saying is that if we're thinking about the domain, just looking at the denominator here, if we factor that, in fact, let's just do that as our first step. What we're going to do is rewrite this as x minus 2 over x minus 2, x plus 2. So if we're just focused on the denominator here, we would say, okay, x can't be equal to 2, and x can't be equal to negative 2. Can't be equal to those things. If we did try and plug those into x, we would divide by 0 and not get any result. So they're undefined at these points. That's for certain. But we notice that if we're looking at just what we have written here, that these actually cancel. There's a factor in the numerator that cancels with a factor in the denominator, and that is a root of the denominator. So if we're looking here, this one x equals 2 is kind of canceling out in essence, and we're left with 1 over x plus 2. So what we can see here is that there is a hole in the graph. Whoops, that's not how you spell hole. There's a hole in the graph where this removable discontinuity is. It is, in essence, kind of disappeared in a sense. It has been removed from the graph. I've seen some different explanations for why we call them removable discontinuities. But if I want to graph this thing, it's going to look very much like the graph of 1 over x. But it's going to be, so here's 1 over x. It looks something like that. But it's going to be shifted to the left by 2 units. So we'll shift it to the left. We'll just pick a different color here. And it's going to be shifted 1, 2 this way. So at negative 2, there's a vertical asymptote. But there's also going to be a hole in the graph at x equals 2. So right here, let me draw that a little better. Right there, that wasn't that much better. There's going to be a hole in the graph. Because it's just simply not defined at that point. So there's no asymptote, there's nothing like anything more interesting going on there, other than there just being a hole in the graph at 2. And at negative 2 is where the vertical asymptote is happening. So those are removable discontinuities. If you get things canceling, factors rather canceling in the numerator and denominator that would have otherwise been an issue in your domain, then those are where the removable discontinuities are. Okay, so finding vertical asymptotes. I mentioned this before. Any restriction on the domain that are not removable discontinuities are where the vertical asymptotes occur. So the graph's behavior near the asymptotes will mimic the behavior of the graphs of 1 over x. So what I'm meaning here when I say this is they'll either around here, the asymptote is at x equals 0. You can see they're going opposite directions, or they'll look like the graph of 1 over x squared, where at the asymptote, the function is headed in the same direction. So they'll either go opposite ways or they'll go the same way. And they could be going the other ways as well. So just to kind of change color here, they could be going, this way and this way, or they could both be headed down. So just different scenarios here. Finding horizontal asymptotes. Here there's just a bunch of different cases that we have to look at. So what we have to look at is the degree of the numerator and compare that to the degree of the denominator. Remember that we're always looking at the ratio of polynomials here. So if the case 1, if the degree of the numerator is less than the degree of the denominator, then there's always a horizontal asymptote at y equals 0. The way I think about that is it's the same as 1 over x. So here the degree of the numerator is 0, the degree of the denominator is 1. 1 over x has a horizontal asymptote at y equals 0. I can always use that to remember this case here. The second case is if the degree of the numerator is greater than the degree of the denominator. Here, there is no horizontal asymptote. So here, if I look at something like x squared, let me write that a little better, x squared over x, what we get is the line x. And x doesn't have a horizontal asymptote, so neither will anything with a degree in the numerator greater than the degree in the denominator. If the degree is only greater by 1, like I've illustrated here, there will be a slant asymptote, and it will be kind of this line that we find. We'll talk about finding slant asymptotes in just a few minutes here. But in general, there is no horizontal asymptote. If the degree is larger on the top than on the bottom, if it's bigger by just 1, then there is a slant asymptote. And then the last case here is if the degree of the numerator is equal to the degree in the denominator, then the horizontal asymptote is at the ratio of the leading coefficients. So if we have something like 3x squared over 2x squared, then the ratio of the leading coefficients, everything else would cancel out. We would just have 3 over 2. It will be at the line y equals 3 over 2. So we'll see some other examples of that right now in action. So the first example here, f of x is equal to x squared plus 1 over x cubed minus 1. The degree in the numerator is 2. The degree in the denominator is 3. This is going to act very much like x squared over x cubed if we just focus on the leading terms here. And this simplifies to look like 1 over x. So I know that there is a vertical asymptote at this line, y equals 0, and there is the picture of this graph. There's some other like bumps and stuff that's going on in there that make it a little bit more interesting, but we know at least that's where the asymptote is. Looking at this next one, h of x here we have 2x cubed minus 1 over x cubed plus 1. So if we just are focusing on the leading coefficients here, I should first say that they both have a degree of 3, so they're exactly the same. And if I look at just the leading coefficients here, just x cubed, what we get is 2 over 1, which is just 2. And we can see that there is a horizontal asymptote at the line y equals 2. So at y equals 2, there is a horizontal asymptote. It is just the ratio of the leading coefficients, since the degrees are exactly the same. All right, if we take a look at this third example here, g of x equals x cubed minus 1 over x squared plus 1. We can see that there is no horizontal asymptote anywhere. Anything that I would draw, it's not really approaching anything, but we can see that there is some sort of something going on here. I think it might be looking, well, not quite like that, but there is this linear asymptote that this thing is approaching on either side. So we have a slant asymptote here because the degree of the numerator is 3, the degree in the bottom is 2. If I looked at just the ratio of the leading coefficients here, we would get just x. So since the function f of x equals x doesn't have a horizontal asymptote, neither does this one. It does have a slant asymptote, and we will talk about how to find that right now. Like we said, if the degree of the numerator is exactly 1 more than the degree of the denominator, there will be a slant asymptote. We find it by using polynomial long division, and we'll look at the quotient. So it is the quotient. The quotient is the slant, is the slant asymptote. We will use that equation and graph that in. It will be our slant asymptote. So here we'll find all asymptotes and graph them. We don't have to graph the actual function, but we might just sketch it in here a little bit. So if I'm looking for the vertical asymptotes, this is going to be anywhere that we would potentially divide by 0, any holes in our domain. So what I'm saying is let's look at the denominator here, and we've got x minus 1. So x minus 1 can't be equal to 0, so that tells us x equals 1 is going to be a vertical asymptote. So let's just get that in here. Put some axes here, and I know I've got a vertical asymptote at x equals 1. So there we go. All right, horizontal asymptote, we would find that by looking at the degree of the numerator and the degree of the denominator. Since the degree of the numerator is more than the denominator, there is no horizontal asymptote. We'll just write no HA since I already abbreviated it that way. But there is a slant asymptote since it is just 1 degree bigger. So the way we find the slant asymptote is by actually doing the polynomial long division here. And we'll divide x minus 1 into 3x squared minus 2x plus 1. And this is how we will find the slant asymptote. So what we'll do here is we'll just divide x into 3x squared and look at the quotient that we would get there, and then we'll multiply it back by the entire x minus 1. So just dividing in here, we're going to get that we will have 3x. So then multiplying back out, we've got 3x times x, which gives me 3x squared. We'll multiply 3x by negative 1, which is negative 3x. And then we want to subtract that entire term. So to me, subtracting everything in the parentheses is the same as just distributing it and then adding the opposites here. So if I think about distributing the negative, I would have plus negative 3x squared plus 3x. And that to me is just an easier thing to do to add than to subtract. So if I'm adding these together now, those cancel out. That's the whole reason that we subtracted. Adding these together here, we get just x. And then we'll bring down the plus 1, and then we'll start this whole process over again. So now we will divide x into x down here. So this is our new kind of dividend. X into x just gives us 1, so plus 1. And then I want to multiply the 1 by everything that we started with here. So 1 times x gives me x. X times negative 1 is negative 1. I want to subtract that entire quantity there. Distributing that, it's the same as adding the opposites to me. So there I distributed the negative, and I can add these together now. Those should always cancel. Here we've got plus 2. At this point, we can no longer divide x into the positive 2. So we've kind of got, I don't know, remainder 2 at the end here. But what we want to look at is the quotient, which is the 3x plus 1. This is the slant asymptote. So when we do this polynomial long division, the quotient gives us the slant asymptote. So that tells us that if I go up to 1 here, we're going to have a point. That's where the y-intercept is. And then I'll go up 3, 1, 2, 3. I'll go over 1. And then I've got this slant asymptote that looks something like that. It is the line 3x plus 1. And then we're not asked to graph the function, but I know that it looks something like this. So you can see it approaching vertically at the line x equals 1, and then we've got this other line y equals 3x plus 1, that is our slant asymptote. So there we go. Not the easiest thing in the world, or the quickest thing in the world, at least compared to the vertical and horizontal asymptotes, but still possible, and we can still find them. You might be wondering, okay, well, what happens if the degree of the numerator is bigger than the denominator, but more than 1? Well, we won't have any slant asymptotes anymore, but we will have something, I think sometimes they call it a base function, or it's just going to be some function that it's approaching. So if you do the division and you get some sort of polynomial function, you get some sort of quadratic function, then it'll kind of approach a parabola asymptotically. And if you get these different shapes, they will approach those different shapes. So let's look at a final example here where we will kind of put it all together and we will graph this rational function f of x equals x minus 4 times x plus 2 squared times x minus 3 all over x plus 1 cubed, x minus 2, x minus 4. So I've got just things off to the side that we should look into to investigate that will help us in sketching the graph here. First let's look for any holes. So that means, are there any? I've already got the polynomials factored. So a lot of the hard work here is already done, and now we just need to investigate the interesting points. So are there any factors in the numerator and denominator that would cancel? So I do see that we have an x minus 4 here and an x minus 4 here. Those are going to cancel, which means that there's going to be a hole in this graph at x equals 4. So, well, I don't know what the output will be, but at x equals 4, there will be a hole. So we'll have to just find that point on the graph once we get it sketched in, and remember to put a hole there. So next we'll look at the y-intercepts. So remember that the y-intercepts are going to be when f is equal to 0. When x is equal to 0. If we plug in 0 to our function, we will find the y-intercept. So remember, like, we're just trying to find a point over here somewhere, and all of these points have x values equal to 0. So we're just going to plug 0 in and see what we get. So if I plug it in here, x plus 2, or 0 plus 2 squared just gives me 2 squared. 0 plus minus 3 is negative 3. If I plug in 0 here, I get 0 plus 1 cubed is just 1 cubed. And if I plug in 0 here, I get negative 2. So if I simplify here, the negatives cancel and I just get positive. This 2 is going to cancel with one of these 2's. That just gives me 6 over 1. So this is just 6. So did a little quick arithmetic there. You can check me on that if you would like. But here I get that this should be up at 1, 2, 3, 4, 5, 6. We should have the y-intercept. And I know that at 1, 2, 3, 4, there's going to be a hole in the graph, and maybe I'll just write the word hole just so I remember to actually put the hole in there once I graph it. All right, next we will look at the x-intercepts and the multiplicity. So let me clean up my scribbles here. I'll still go back and cross out the x minus 4 since we're done with those. If I'm looking for the x-intercepts, this is going to be anywhere where the output is 0. So somewhere it's crossing over here is going to be where the entire function is equal to 0. So we're really going to be looking at, well, where is x plus 2 squared times x minus 3 equal to 0? And that's what we're trying to solve here. So let me actually maybe scoot that over to give myself some space to write down what the actual answers are, but this is the idea. And this is going to be at x equals negative 2. We'll have an x-intercept, and the multiplicity at that point is 2, which means we're going to have some sort of a bounce. So I can even come put that in over here now. Here's negative 2. I know that it's either going to bounce like that or it's going to bounce that, and it just depends on the direction that it's going to be coming in, and we'll have to think about that once we go in to sketch our graph. And I can see that there is another x-intercept at 3. So at x equals 3, there is an intercept, and this has a multiplicity of 1, since there's just a 1 here, which means that it's going to just pass right through. So over here at 3, I know that it's just going to pass right through. So I'm just making a few marks on my graph here of things that I know are going to happen, and that'll help me when I go to sketch the graph. Okay, so I've got the hole marked, I've got the y-intercept marked, I've got the x-intercept marked with their multiplicity, so I know what behavior happens near those intercepts. Second to last, we've got the vertical asymptote. So this is going to be any holes in the domain that aren't removable discontinuities. So meaning I'm going to look at the denominator here and think what those values would have to be that we need to remove from the domain. So if we're looking for the vertical asymptotes, they're going to be at x equals -1. Since there is a cube there, that means since we have an odd power here, it's going to act kind of like the graph of 1 over x cubed, which they go opposite directions. So I'm just using what I know about 1 over x cubed to think about what's going to happen, the behavior around this vertical asymptote at x equals -1. And then the other one is going to be at x equals 2. That also has an odd power on it, so this is also going to be opposite directions around that point. And if you're not quite sure what I mean by opposite, I'll make sure to point that out when I sketch them in here. But, well, actually, I'll just sketch them in right now. So I know that there's a vertical asymptote at -1. So here's a vertical asymptote at -1. And I know that the behavior is either going to be going up here and down here, because that is what happens for 1 over x cubed, or it'll be going up here and down on this side. We just don't know which is the case yet, but we will determine that here in a second. And then the same thing at x equals 2. I have another asymptote. So we can deal with that in just a second here as well. Okay, horizontal asymptotes. What do we have here? Let me go unscratch things out. Delete. Okay, so the degree in the numerator is 1. So even with the things not canceled out, we've got 1, 2, 3, 4. So degree 4 in the numerator. And we've got, was that right? 1, 2, 3, 4. Yeah, and then the denominator, we've got 3, 4, 5. So degree 5. Which tells me that this is going to act a lot like x to the 4th over x to the 5th, which is 1 over x. So since the degree in the numerator is smaller than the degree in the denominator, we know that this will have a horizontal asymptote at y equals 0. I can justify that to myself by thinking about just what the leading terms, what their behavior looks like, and that's the same as 1 over x. So I'm convinced that there is a horizontal asymptote at y equals 0. Okay, so I think we have enough information to try and get a graph sketched in here. So maybe I'll do this in a different color. Let's do green or something. Since I know, and this is where we have to start using some logic, and it's not always clear where we should start. We know where things are going to happen in some certain spots here. There is no anything over there. That was a random mark. I do know that there is a vertical asymptote. I'm sorry, a y-intercept up here at 6. I also know that there are no x-intercepts in this interval between these two vertical asymptotes, which means it never crosses. So that means that the only thing that it can be doing is something like this in this little neighborhood. I know that the function's defined there. It needs to live completely above the x-axis, and it needs to be getting asymptotically close on both sides to the left of -1. I'm sorry, to the right of -1 and to the left of 2. So that's about the only behavior that could happen there, so I will get that sketched in. Now I'll think about what's happening near this vertical asymptote. Since at -1 we have opposite directions, that means that it must be going down that direction, and I'm gonna have to scoot that over a little bit, but it's going down that way, and it must be coming up and bouncing off of the line y equals 0, off of the x-axis, and then coming down, and then I know that the horizontal asymptote is the x-axis here. So it must be bouncing and then coming back and asymptotically approaching, but not crossing again. Since there's no other x-intercepts over there, I know it's not crossing anymore. But that must be the behavior over there, and I know that it is just touching right there at -2. This is -1. This is obviously 0, 1, 2, 3, and 4. Okay, so then what's going on over here near this other vertical asymptote? That's also going opposite direction, so it must be coming up this way. It must be passing through because of the multiplicity at 3 just being 1. And then I know it must also turn around and approach going that way asymptotically, and then I need to remember to put in a hole here. So I've got a lot going on here, but I didn't mean to erase that whole thing. What I need to do is remember to go put in my hole right here, because there's a hole in the graph at 4. So I need to remember to put in that hole in the graph. So I think, there we go. Not the prettiest looking graph in the world, but we've got it. We've got things marked here. We can see it approaching the asymptotes where we expect them. We've got, maybe I'll just label everything on here. This is the line x equals 2. This is the line x equals -1. This is the line y equals 0. There we go. So there is a rough sketch of this graph with things kind of marked where we would expect them to be. All right, with that, it is time to go practice. So I wish you well with your homework. Please let me know if you have any questions, and I will see you in the next video.